So we now want to look at the solution near a singular point and near a regular singular point, not all singular points, and so we need to define what we mean by a regular singular point. And so to complete the terminology, we may be interested in what is the opposite of a point which is not a regular singular point but also a singular point. That would be an irregular singular point. This is not regular and singular don't negate each other. Singular points come in two categories, and so let's define what we mean by a regular singular point. So let's look at the equation that we had before: capital P times y double prime, capital Q y prime, capital R times y equal to 0. X equal to x0 is a singular point, as we have defined before, if this coefficient here, P of x, vanishes at x equals x naught. And it is a singular only when this vanishes, but either Q or R or both don't vanish at the same point, because if they all went to 0 at the same point, we can cancel that behavior out by dividing still. And that would be sort of like if you think about L'Hopital rule in algebra, that factor would cancel out of the equation entirely, but they simultaneously don't vanish where P vanishes, and therefore there is something singular going on. If you think about dividing the rest of the equation by this, and so we will have a behavior which will cause something interesting to happen. And so a singular point is called a regular singular point if these additional conditions are satisfied at x equal to x0, namely that this division blows up, but this division times x minus x0 does not blow up. This has a well-defined limit. And likewise, this ratio r over p blows up, but x minus x0 squared times r over p is well-behaved. And so when these are well-behaved, then these products have well-defined Taylor series expansion. They are analytic functions near x equals x naught. And so that's a property that will be useful later on. So we have so far talked about singular points being at arbitrary position, and so to simplify things, we are going to shift the singular point to a new location, and so we shift the independent variable, define x minus x0 equals z as a new independent variable, and so then the singular point will shift to z is equal to 0, as is obvious from the definition. And so in proceeding further, we're going to assume that z equal to 0 is a regular singular point. All right? And so now we're going to rewrite this differential equation in terms of z. So the second derivative with respect to z, function p of z divide dz, q of z times y equal to 0. And these functions p and q that appear in the equation are given by these ratios that we had encountered before. They are simply functions of z, and z equal to 0 is the regular singular point that is of interest. And so P and or Q are going to be singular because Q is divided by P. Q does not vanish, let's say. P vanishes, and so this ratio is going to blow up, and that's what we mean by P and Q both being singular, one or both being singular. But it being a regular singular point means that z times P of z and z squared times Q of z are not singular, they are well behaved, and so they have power series expansion, a regular Taylor series expansion with integer exponents here. P0, P1, P2 are coefficients of a Taylor series expansion of the product z times P of z. And for the product z squared times Q, there is a power series expansion with coefficients q's that are indicated there. So these are going to be used to come up with a solution for the differential equation. And so let's see how we can make use of that. This is the differential equation, and so let's pre-multiply this equation by z squared, and then we are going to rewrite it. And so you can see that this term is simply rewritten like this since we multiplied by z squared. And when we multiply the second term by z squared, we can split those two powers of z in this way, one z outside and the other z inside. And the reason we are doing that is because z times P of z is a regular function, as we have just noted. And of course, we have z squared times Q of z, which is a regular function. So at this stage, this equation is ready to accept a power series type solution. And so, of course, the thing is that in the original equation, P and Q are singular, possibly both singular, and therefore we cannot have the behavior of the solution as being a regular solution, and so we have to have some kind of singular behavior possibly for one or both of the homogeneous solutions to this differential equation. And to find what kind of behavior is permitted by this differential equation, we need to permit this behavior in the series solution that we seek. And so that is the Frobenius method. And so we seek a solution of this form. We say that y of z is a series expansion, but the series expansion with the regular integer valued coefficients here for exponents is pre-multiplied by z to some power r, which is an unknown exponent. And so in particular, for example, if we have r as a negative number, then this series is going to blow up as z goes to 0. So the solution will become singular as z goes to 0. But at this stage, we say r is an unknown exponent, and we're going to have a method to determine r. And so we're just rewriting this by absorbing this power inside. And so we can simply say that sum ak as the coefficient, z raised to r plus k, we just brought this power inside, and so we can write that. And so at this stage, we are ready to take derivatives, and so we are taking derivatives just as we did before. But since the power is r plus k, this factor shows up here when we differentiate it once, and power reduces by 1. And so when we differentiate one more time, then this factor gets put over here. This is carried here, and so this is the expression for the second derivative. And so now we have an expansion for the function, its first derivative and second derivative, and we have expansions for z times p and z squared times q, which are the coefficients appearing in the equations. Of course, this z and z squared are already nice powers of z, so we are in a position to substitute all this in the ODE, and so that's what we're going to do. We're going to substitute this in ODE, and in terms of guiding that discussion, let's remember that what we're going to do is we're going to insist that once we substitute all this, that we have a non-trivial solution. And so non-trivial solution will require that the leading order coefficient a0 does not vanish, and this will then allow us to find this unknown exponent r, and then it will allow us to also find the coefficients a sub k's. So that is the next thing that we're going to do.